Hello and welcome to week 13 in Algebra. We are going to do a couple warm-up problems, so as always, stop to make sure you've got your math notebook out and you're ready to take good notes. Remember, these notes are to help you with learning the material better. So taking notes by hand really does improve the learning. So that's why I ask you to do that. And in your math notebook, I would like for you to start with two warm-up questions. The first one, you are going to calculate or evaluate 5 to the third power, or sometimes we say that is 5 cubed. And then the next warm-up problem is 6 to the 1/2 power. So go ahead and click pause and try these on your own. When you're ready to check your work with mine, go ahead and click play. So click pause, try it on your own. When you're ready to check your work with mine, go ahead and click play. Alrighty, so 5 to the third power, or 5 cubed. Remember, this is not saying 5 times 3. That is not what powers mean. So when we have an exponent, it means that we're going to multiply that base number 5 times itself 3 times. So that's what the exponent means. We're going to take that base of 5 and multiply it by itself 3 times. 3 times. If I said 5, I meant to say 3 times. We multiply 5 times itself 3 times. And what do we get when we do that? Well, I know 5 times 5 is 25. So multiply 25 times that third 5, and what do you get? You should get 125. So just a reminder what exponents mean. We are going to be looking at exponents this week, so I did want to do a quick review of what exponents mean. So now we've gotten this second one, 6 to the 1/2. So we have a fraction. We have a fraction as our exponent. So this is just a fancy way of saying that we want to take the square root of 6. So 6 to the 1/2 is the same thing as saying the square root of 6. And remember, when we're trying to find a square root of something, we're trying to find what number times itself would give us 6. And in this case, there isn't a whole number that would give us, that when we multiply it by itself would give us 6. So I'm just going to leave the answer as the square root of 6 because that's the most exact answer. If I were to type that into a calculator, the square root of 6, I'm going to get a decimal, and it's a really long decimal that eventually I would have to round because I think it's, let me plug that in really quick, it's 2.4494897. It keeps going. So most likely I would end up rounding that to 2.4, which is not the most exact answer because I did some rounding, right? So I think in this case, the best thing to do is just leave it as a square root of 6 because that's going to be the most exact answer. All right, so moving on. What are we doing this week and what are we going to see a preview of today in this recording? So this week we are finishing up Unit 3. We're going to take the Unit 3 test. Then we're going to take a pretest. Remember, pretests, you're going to get full credit no matter how you do. Pretests are a great way for you to see what is coming and what you're going to learn, what you might already know. And if you don't know something, that's okay. And what's really cool is at the end of the unit to see how much you've learned in Unit 4. So Unit 4, we're going to start with looking at exponential functions as well as geometric sequences. So remember in Unit 3, we looked at arithmetic sequences where we increase the same amount by adding or subtracting to the previous number. So it's a pattern that we're adding or subtracting the same amount to each term. Where geometric sequences are a little bit different than arithmetic sequences. And you're going to learn about what makes a sequence a geometric sequence this week. So let's jump right in. Some tips. I know we're getting close to the end of the semester, so I wanted to go over some tips to help you guys get to your goal grades. So first of all, make sure you're checking your grades often so you know where you stand in the class. Then, not only should you be checking your overall grade, but look to see how you did on each individual assignment. And don't stop there. Click on the graded assignment, that score, and then view the assignment to see what you missed and what you got correct. And remember, I'm always leaving feedback on those questions that you missed so that if you want to do a redo, those can help you. Check your updates daily, and just a reminder, make sure you're reading your emails and messages daily. All right, so let's jump in with geometric sequences. So again, remember, arithmetic sequences were when we had a sequence where each term was increased or decreased by adding or subtracting the same amount each time. Where now geometric sequence is that should say ratio between any two a sequence in which the ratio between any two consecutive terms is constant, called the common ratio. So now instead of adding or subtracting, we're going to find that there's a ratio. And remember, ratios are when you're comparing two numbers and it looks like a fraction. So here's an example of a geometric sequence. So remember, when we looked at arithmetic sequence, we would compare the term with the term before it to see how it had changed. And we're going to do the same thing with a geometric sequence. So what I'm going to do is I'm going to look at this second term and compare it to the first term. Now, because it's geometric, there's going to be a common ratio between those. And a ratio, remember, is in a fraction form. So if we compare 3 to 1, we can say how much bigger how did we increase from 1 to 3? Well, if I already know this is a geometric sequence, I'm kind of cheating. So I just compare, I write it as a ratio, and I'm comparing 3 over 1. So I know that it increased 3 times as much. And then I can check that pattern. So from 3 to 9, if I multiply 3 times 3, I get 9. If I multiply 9 times 3, I get 7. So the common ratio is that we're multiplying times 3 between each of our terms. We're multiplying times 3 between each of our terms. So the common ratio would be, of this sequence, would be 3. And again, I can figure that out by, first of all, I know it's not arithmetic. It's not an arithmetic sequence because it's not increasing by the same amount each time. It's being multiplied. And to find that common ratio, you take the second term and divide it by the first term. Or you can take this term and just divide it by the term in front of it. As long as you take a term and divide it, or set up a ratio, I should say, it's not necessarily dividing, set up that ratio of the term in front of it, like 27 over 9, and that reduces to 3, that's going to be your common ratio. So look at this second example where our sequence goes 4, 16, 64, 256, 1024. So again, these aren't increasing. These terms are not increasing the same amount each time, so we know it's not an arithmetic sequence. So we know it's going to be geometric because it's increasing by either multiplying or dividing. So in this case, it's getting bigger, so we know we're multiplying. So how would we go from 4 to 16? Well, if it's not easy to see, just take that second term and divide it by the first term. What do you get? 4. That should be the same amount if you take the third term and divide it by the term in front of it, that second term. And what do you get? 64 divided by 16 is 4. So it's the same amount. So we're multiplying by 4 when we go from each term to the next term. So that would make our common ratio in this sequence would be equal to 4. So now I want you to try And look at these next two sequences and tell me the common ratio. So remember, you're only going to have a common ratio if you have a geometric sequence. So go ahead and click pause and try these next two problems on your own, the next two sequences. Find the common ratio of each sequence. All right, so what I'm going to do is I'm going to compare the second term in a ratio to the first term. 6 divided by 2 is 3. So it looks like if I multiply each term by 3, I should get the next term. Does that work? 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 64, or I'm sorry, 54, so that works. So the common ratio in our first sequence is 3. What about the next one? This time we're going to need smaller. So in order to get smaller, we would have to be multiplying each of our terms by a fraction. So again, we can figure out the common ratio in the same way. If I take the second term, 40, and divide it by the first, or set up a ratio comparing it to that first term, we get a fraction. And I can reduce that. What looks like we can cross out the zeros, and we've got 4 over 16, which reduces to, we can divide out a 4 of each of those terms, reduces to 1/4. So our common ratio of our second sequence here is 1/4. So if we multiply each term by 1/4, we'll get the next term in the sequence, and that works, right? 40 times 1/4 is 10. So I'm going to move on, so if you need more time, go ahead and click pause. All right, so sometimes you might have a geometric sequence where you're given the first 3 numbers of the sequence or the first 4 terms in the sequence, and you're then asked to find maybe the 20th term or the 30th term of that sequence. So we know we could do that if we know the common ratio. We can just keep multiplying that the previous term by the common ratio until we get to whatever term we're looking for. But if we're looking for like the 20th term, that might take a pretty long time. So lucky for us, we have a formula that we can use to find higher number terms, like the 100th term of a sequence. We have this formula right here that allows us to find any term in a sequence pretty quickly. So here's the formula. You might be looking and saying, wow, that's a lot of strange looking letters and whatnot. So let's go through this and make it a lot easier than it might look. So a to the n, this represents the a to the n is the nth term. It's whatever term you're looking for. So it's the 10th term. If you're asked to find the 20th term, if you're asked to find the 30th term. So this formula is going to give you whatever term you are asked to find. And I put nth because it could be anything. It could be the 100th term. It could be the 30th term. But whatever term you're looking to find, it's going to be equal to a to the 1 represents term 1. It's the first term in your sequence. So a to the 1 represents your first term. So if you're given your first term of a sequence, or a couple of them, the first term is going to be represented by this a sub 1. R represents the common ratio, and we learned to find the common ratio on the previous slide. So the common ratio we find, remember, by dividing a number by the previous term. That's your common ratio. And then n minus 1, n, remember, represents the term you're looking for. So n represents the term number you're looking for, the term number. So it always makes a lot more sense when we use it in an example. So let's do just that. So we've got a geometric sequence, 2, 8, 32, 128, 512. We want to find the 10th term. So instead of finding the common ratio and multiplying it by each term till we hit the 10th term, which would take a long time, let's use this formula. So the first thing that we want to do is we want to find or identify the common ratio. So we know how to do that now. So we can take any term and divide it by the previous term. And that's going to be our common ratio. So I'm going to take the second term and divide it by the first term. So 8 divided by 2, and that gives me 4. So the common ratio, which is represented by R, is going to be equal to 4. I want to find the 10th term, so let's start plugging into this formula. So A, I want to find to the, instead of putting N, I want to find the 10th term. So I'm going to say A sub 10 is going to represent that I'm finding the 10th term, is equal to, what's our A1? That's the first term in our sequence. First term in our sequence is 2. So I'm going to plug in 2, and then I'm going to multiply it times R. If I want, let me go ahead and put up the original formula here so I can see what I'm substituting in. All right, so R is the common ratio, which we determined was 4, and we're looking for the 10th term. N represents the term number we're looking for. We're looking for the 10th term, minus 1. So let's clean that up a little. 10 minus 1 is actually 9, so we're going to take that to the 9th power. So to find the 10th term, now we've got an equation set up for us. This is important now that we remember PEMDAS, order of operations. So PEMDAS, the P represents parentheses, the E represents exponents. So we need to evaluate any exponents first. So we're not going to multiply 2 times 4. That would not give us the correct answer. We need to first find, evaluate that exponent there. So we need to evaluate 4 to the 9th power, which we know is the same as 4 times 4 times 4 times 4. 4 times itself 9 times. So I'm just going to plug that into the calculator. I'm going to say 4 to the 9th power, and that gives me a pretty large number. It's going to give me 262,144. And then we're going to take that number and multiply it by 2. So this is going to give us our 10th term. So when we do that, 2 times that 262,144, and we get 524,228. And that represents the 10th term. A sub 10 represents the 10th term. That's our 10th term. So that would be our final answer. Pretty big number, right? But pretty quick way of figuring out what the 10th term is. So you're going to do some more of that on your own this week. Make sure you copy down this formula to find the nth term or any term in a geometric sequence. So write that down, and then also be sure to write down what each of these terms represents. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. All right, so now we are going to look at exponential functions, which are kind of similar to geometric sequences, and we're going to learn why those two things are similar. So we know a lot about linear functions, right? It's like an arithmetic sequence. In linear functions, our terms increase the same amount each time. So if we're given a table with x and y values, the y you can think of as like the terms, and the x's as like the term numbers. So the initial term 2, the value is 2. The first term, the value would be 6. The second term, the value is 10. We can see each time it's increasing by 4, right? We're increasing the same amount from one y value to the next. And we know when we graph linear functions, we get a straight line. So let me graph this really quick. So because our y values are increasing the same amount each time, we get a straight line. When we graph a linear function, we get a straight line. Now, exponential functions are a little bit different. And again, I said they're kind of similar to geometric functions. Why would I say they're similar to geometric functions? Look at our y values. Are they increasing by the same amount each time? 4 to 8, 8 to 16, 16 to 32. Well, they're not being added by the same number, but they are increasing by multiplying each of our terms by 2, each of our y values by 2. If we multiply them by 2, we get the next y term. But what does it look like when we graph it? Is it going to be a straight line? No, it's not going to be a straight line. What shape are we going to get? So let's go ahead and graph this. So 0, 4, 1, 8, 3, 32, so it's going to be way up here. But the shape that we're going to get, I didn't use a good coordinate plane, but the shape we're going to get is going to look more like this, where the increasing starts out to be slowly, but then over time, the amount that it increases. So we get this shape of a graph like this. So when we have exponential functions, the graph shape is going to look more like a half U shape. So just wanted you guys to see what the graphs look like when we compare linear functions to exponential functions. And then the idea that when we have exponential functions, it's not being, the values between our y's values are increasing by being multiplied by the same amount each time. That's what an exponential function is, which is also very similar to our geometric functions, weren't they? Our geometric sequences. So now that we know that, we should be able to look at a table and determine if the table represents an exponential function by comparing the y values. And remember, the y values have to be multiplied by the same amount between each of our terms in order to be an exponential function. So is that happening here? Let's look. How do we go from 2 to 6? Again, it's got to be, in order to be an exponential function, it's got to be being multiplied by the same amount. So terms have to be multiplied by the same amount. And remember, they can be getting smaller. If our terms are getting smaller, we would be multiplying by a fraction. We would be being multiplied by a fraction if we're getting smaller. If we're getting larger, we're being multiplied by a whole number. So how do we go from 2 to 6? Well, 2 times what gives me 6? 2 times 3. Now, if this is an exponential function, that would have to be the same amount when we go from term 2 to term 3, or from this y value to the next one. 6 times 3, does that give us 18? It does. What about 18 times 3? Does that give us 32? 18 times 3, does that give us 32? It does not. So this right here kind of messed us up. So this is not an exponential function. So again, when I say terms, I should say this is our y values. Our terms here are our y values. So the y values are being multiplied by the same amount in order to be an exponential function. So I put x there to say multiplied. All right, and we determined it looked like it was starting to be an exponential function because we could multiply the first couple y values times 3, but then right here we saw that from 8 to 32, we are not increasing by a multiple of 3, so that is not an exponential function. I'm going to go on to the next slide, so if you need more time, go ahead and click play. And that's a wrap. So let me put up the key phrase assignment. Alrighty, so we learned what geometric sequences are. We also learned how to find the common ratio of a geometric sequence. So I've got a geometric sequence, 7, 21, 63, 189, and I would like for you to tell me what the common ratio of that geometric sequence is. Have a great rest of your week, and if you need any help with anything, let me know.